Today's session is about EDR and how they actually place their hook to detect you. So the idea is from an attacker perspective, we're trying to get rid of the hook and successfully execute code without being detected. We're gonna go inside of the Windows Core API and see how it works. We kind of covered that in previous session, but I'll once again kind of give you an idea of what it looks like from an attacker perspective and how we can actually defeat the protection in place. So to start with, I'm gonna actually use the proof of concept that we wrote 1 or 2 classes ago, which was a simple process injection, right? No need to tell you that this code will be detected by the EDR for various reasons that we'll cover later on, but these are obviously Windows API that are highly dangerous, right? The one that we're going to look at is actual virtual unlock for now, which tend to be hooked by EDR. So we're actually going to look at the code and what it does in the background, and we're going to look at the same piece of code in a VM that actually have a EDR running. So without further ado, we have the actual code here. This one, which is the create remote thread, right? And we're gonna break on the virtual lock ex call. We're gonna run it, and eventually we're gonna get to that point, right? Nothing fancy here. If you remember, we're inside of kernel 32. As I pointed out, kernel 32 is most of the time just used as a bridge between the actual code. So this is pretty standard to see a jump. Interesting things, I've mentioned this in the past. Back then, some EDR actually used to override that jump with their own jump. So instead of jumping in the actual code, you were just jumping inside of the EDR code, right? So that was a easy way to hook it. But as you saw in the past, if you actually, implement the syscall yourself or use the NT version of the actual API, you're literally gonna jump on top of the hook. So EDR kind of changed the way that they actually do their hooking to avoid that. So this jump here is still legitimate. We're going inside of kernel base, nothing special here. Once again, internally, kernel base will call virtual alloc ex numa, which is once again just a Windows API inside of kernel base. Kernel base will do more preparation. And finally, we're going to jump to the lower level API, which is NT allocate virtual memory, right? Remember when we talk about the syscall thing, this is pretty much where we are. So this is the closest to the kernel that we can get from user mode. Basically, syscall is just going to issue the call to the kernel, and you're going to get the output out of it. Remember, syscall require you to have a specific ID. So this is what the move EX does. Each syscall have a unique ID, so we're gonna have to keep that in mind in the future. So I'll just pause the debugger here at that specific location, and what I'll do is actually look at the same code inside of the VM where the EDR is actually running as we speak. It's also important to note that if you want to see if there's some potential program, look at your code. Look at the module. It's usually a good sign. If you look at this one here, we don't have anything fancy. Kernel base, kernel 32, MSV, CRT, and NTDLL. Nothing really suspicious. That's also a good indicator that there may be something going on, and you're gonna see it right away with the code running inside of the VM. So first thing that we notice here, we have this extra DLL UMPPC12806, and we have the other DLL. So this is usually a good sign that may be something going on. And if you want to validate what this DLL is about, I highly recommend that you literally just use the UI and check the description of it. So we have the path in IDA, which is quite nice. So let's go take a look at the file itself. UMP. Here it is. Right click on it, property and details, file description, CrowdStrike Falcon sensor support module, CrowdStrike Falcon sensor, CrowdStrike. I think it's pretty obvious that this DLL is related to CrowdStrike, which kind of give you an idea of which EDR is running on that specific instance as we speak, right? So that's a good sign that there's something that we didn't ask for that's been loaded inside of the process that we actually ran. So let's dig inside of virtual log EX once again. So nothing fancy here. Kernel 32 once again, we're gonna jump in here. they could have actually hooked that jump, but they're not, because as I pointed out, if you actually call directly, the virtual alloc EX NUMA, you're literally going to bypass the whole hook. So they're trying to keep the hook as lower as possible in the chain. So nothing has changed here. We're going to call the other portion, which is virtual alloc EX NUMA. And at some point, we're going to get ready to actually call the NT allocate, which is here. So let's jump into it. And here we go. We are at NT allocate virtual memory. Remember we had the syscall thing. Notice that it's actually gone now and we have a jump instead, which is a good sign that there's probably something that was hooked, right? And we can actually confirm that this jump is, from our perspective, malicious in the sense that it's probably the EDR that is in place by simply following the jump, right? As you can see here, we're still in NTDLL. It was kind of, a code cave that they used to prepare all the stuff before they actually jump to this location here. As you can see, they're just pushing information, then they're going to jump to that offset. Notice that we're now in the UMPPC12806 DLL. So it is a good sign that it's usually been hooked by an EDR. So let's just restart it again so we can compare both code. And here we go. I'm going to try to put them side by side as much as I can. I guess that's probably the best I can do. Let me actually do it the other way around. So as you can see, move R10 RCX, move R10 RCX remain the same. Then we have this move EX18, which is the ID for the specific syscall related to allocate virtual memory. And you have the syscall. In this case, we have a jump. So obviously this function was hooked, right? So as part of the exercise, I wanted to actually get a list of all the potential hook functions. And what I did was actually rely on the fact that the code will change, right? So if you look at it from an opcode perspective, on both sides, you'll notice that it's fairly easy to fingerprint it. We know that the structure is always going to be the same, right? So it's always going to be move R10, RCX, then we're going to have this move EAX and whatever arbitrary number. In this case, the first part remained, but we have this jump that was added. So if we look at it from an opcode perspective, 4C8BD1 remain, 4C8BD1 remain, and we have this E9 instead of B8, right? So the fourth byte after the beginning of the function is a good indicator uh, to look for hooks. Keep in mind that if we do that against, kernel 32, you're probably going to get like a list of functions that were hooked, even if they're not, because most of the kernel 32 export are actually just jumping to kernel base, right? So we have to kind of pick and choose the right DLL. I'm not going to write the code to actually list all of them. I'm just going to show you the code that I write this week because we kind of already did that. I used the same concept as what we did when we actually resolve all the exporting and DLL using shell coding. The only difference is I just ported it to pure C. So here it is. Let me actually just put it in code block. So as you can see here, we have the checklist of exports. So it's pretty straightforward in the sense that we're going to actually pass a library as an argument, and we're going to actually load that library. As you know, it's just going to retrieve a pointer to the beginning of the library. Nothing special here, so we're going to be at the beginning of the MZ. And if we look at it, let's pick NTDL as the example. The pointer that we'll retrieve will actually point here, which is the beginning of the MZ header, right? So from there, what we need to retrieve is the PE header, right? So it's fairly simple. The base is literally the address, and we know that the PE offset is always going to be located at 3C as shown here. Once again, this is typical structure. This is the MZ structure. So this is what this cut does here. It just retrieves the offset here, which is actually the value shown in the CFF Explorer. So at this point here in PE, we have the offset of the PE header, which is base plus whatever it's at this offset, right? So PE is going to point to this structure here. What we need afterward is to actually get to the export directory offset. Once again, we kind of covered that when it comes to casting. Remember that if you do like an addition on an actual pointer, it's gonna take the type as the size. So the word is 4 byte. That's why I'm actually dividing it by 4 to make sure that the compiler will give me the right value. If I don't divide it by 4, it's just gonna multiply whatever number I feed it here by 4. It's just gonna get it a bit confused. So eventually what's going to happen is we're actually going to land into the export directory address. And once again, we're going to get that specific offset here, which contains that value. So once again, we're going to start by making sure that we actually get the address of the structure. So it's always going to be base plus that offset, right? So this is going to be feed in that specific variable here. Here's just the actual offset. So we're just doing the math later on. So base plus this offset. At this point in time, we have a pointer to this here, which is telling you where the export directory is, which is exactly located here. Once again, this is done all dynamically, but at the end of the day, what we're doing is like the math to get to the beginning of that structure. One of the things that we need to know in this case is the amount of function, because we want to make sure that the code will not crash, right? And fortunately for us, there is a numbers of function element in there, which contain the number of exported functions. Fairly simple. Once again, we can just calculate the offset. So when we get the offset to the export directory, we can easily just rely on this and do the math. So once again, you take this specific offset here and you just do the math to figure out what is the difference between them. And you're actually going to get the address of the numbers of function, and you're going to retrieve the value one more time. So once again, what we're doing here is cast it as a D-word pointer. Then we're actually going to have the offset that we need, which is 14x, and we're going to divide it by 4 because the compiler will basically multiply this by 4 for you because the word is a size of 4. So when we get to this address, we're going to dereference it. The point is to actually get the value, not the address of where the value is, right? So in this case, we're going to get the actual value being set in this variable, which will tell us how many functions are available in that specific DLL. Then the last thing that we need is the actual offset name tables. So this is where all the function name are actually located. And you have it here, which is address of names. And once again, it's just a pointer that will point to the list where all the functions are actually located. So once again, you just do the math, you'll notice that it's a bit bigger than number of functions. So it makes sense, right? This one is 14, this one is 20, which is just pointing to the right location. Once again, we're using the same divided by 4 trick to kind of trick the compiler because we're using a D-word size. Then we can calculate the offset name table dynamically, which is base plus whatever offset we got from the PE header. And at this point, we do have a pointer to an offset table. This is exactly what we're looking for because now we can actually go through all the exported functionality in there. The idea is that we're actually going to resolve them at runtime and see if the signature is matching anything that looks like it's been hooked. So after we retrieve all this information here, you're just going to do a for loop based on the function count -1 because it tells you that there's like 7E functions, but keep in mind that it's really important that it's always going to be the number, so it starts at 0, so it's always going to be -1. Then you're just actually going to loop through it, and once again, it's fairly easy. If you want to know what is the name of it, you just calculate base plus offset because that's just how it is, right? It's going to tell you the offset of where the actual text is located, and you're going to actually get the name, right? So current is now holding the name of one of the export. So what we need to do now is to actually resolve that API and see what's up with it, right? So this is what get bytes by name actually does. You pass the endl to the DLL because we're obviously going to need to do a get proc address call and the actual name that we need to resolve, right? So get proc address is going to use the endl to the DLL, which we retrieve in the main, right, with the load library, and we pass this as a parameter to the underlying checklist of export. Then checklist of export is passing it to get byte by name, right? Nothing special here. It's pretty standard way of passing arguments to functions. Then what we're going to do is actually take the first 4 bytes that are located at that address. In this case, the address is stored in PTR. So what we want to do here is actually get the upcode, which is going to be a dword pointer. So we're going to dereference the pointer to get what's inside of it and just do a little bit of casting magic. Excuse me. And here what we're going to do is actually check the byte to see if the 4th byte is actually E9. If it is the case, we're probably facing a hook. And to make sure that we're actually facing a function that looks like what we're expecting, we're also going to look at the first 3 bytes, right? In this case, we know for a fact that the first 3 bytes should be these 3. This is basically a sanity check to avoid a false positive, right? So this is how we actually come up with that code right here. And if we pass both check, it means that we're obviously looking at a function that was hooked by the EDR in place. So usually what you do is you run this against the DLL like NTDLL and you kind of wait for the result, and actually posted the result in the GitHub project. And as you can see here, as I mentioned, you have the information. So the base is at this address, and I even dump it so you can see the MZ header. Then the calculation to get to the PE, which is basically base plus whatever offset is located as 3C, which can be confirmed here. Offset 3C contain E8, so it makes sense. You know, it was base plus E8. Then the export table offset is just, more mass. Offset name table is just more math based on, the information that we retrieve here. So that's why the number are kind of growing bigger. And you also have the function count, which once again can be confirmed. You have the number of function, which is 97E, which is 97E. So we successfully retrieved the right information. Also converted this into decimal, so it's just easier for human to understand this actual number. So there's actually 2,430 function exported in NTDLL. Then it's going to perform the check. So every time the check is successfully passed, it's going to return the name of the API and tell you that it's hooked. So for CrowdStrike, for example, this is the list of API that they actually successfully hooked. Here's the one for Sentinel-1. Notice that there's quite a lot of them compared to CrowdStrike. And funny thing is like LDR load DLL is hook, and it's usually called by load library. So they're probably trying to take a look at what you're calling using load library from a Sentinel-1 perspective, which is interesting. CrowdStrike is much more lean when it comes to hooking. They're still hooking, what we considered valuable, especially when it comes to process injection. So you have the NTQ, APC, resume thread, and all that kind of stuff, allocate memory. So it is pretty typical. Notice that you also have the NT version and the ZW version of it. So NT allocate virtual memory here and ZW allocate virtual memory. You may remember I kind of talked about that in the past. The idea is that these are actually the same functions, and you can easily confirm it by looking at the NTDLL itself. My understanding, based on Microsoft documentation, is that ZW should be used when you're doing kernel code, and NT version of it should be used when you're doing user mode code. So what we're doing right now is user mode code. It's just for clarity, I'm assuming. So NT allocate. So NT allocate virtual memory is located at C2A0. And as you can see here, we have the syscall code, nothing fancy, nothing special. And if we actually look at ZW, it's also here, and it's also pointing at C2A0. So they're technically like the same function, they just have a different name because they're pointing to the same location in the code. And as you can see, the debugger is kind enough to kind of tell you that the export entry is 220 because you can always use the ordinal representation of a function. So it tells you that NT allocate virtual memory have the export entry 224 and the ZW have the entry 1807. But at the end of the day, they're both pointing to the same location. That's why you kind of see it that way, right? So they're literally just pointing to the same location. And this is something to keep in mind because I've seen some posts that says that use the ZW version of it and you're going to bypass, some security measure, which is obviously untrue because as you can see, they're literally pointing to the same location. So, uh, fact check is always a good thing to do. So that being said, we are now at this specific point in time where we kind of know which kind of API we're looking for, and we kind of know that these are obviously hooked by the EDR in place, right? So in the case of something like dumping LSAS memory, the idea is to actually make sure that you're going to be able to remove the hook on the specific function that they're going to use in the background. And that's exactly what we're going to do here. We're going to re-implement the mini dump code, uh, which is pretty straightforward. Once again, it doesn't do anything special. Mini dump is actually a high level API in the sense that mini dump write dump is an API that is exposed in dbg help.dll, but in the background, it's obviously going to end up calling some internal Windows NT stuff, and we're going to discover which one it is by using API monitor later on. Uh, just for your information, Minidump is really not doing anything special. All it needs to do is open a process with a PID. So obviously in this case, it's going to be LSAS. It's going to retrieve an handle to create a file. Keep in mind that it may be confusing, but create file does not create a file, just create an handle to a file. You're basically specifying the flags that you need in there. In this case, it's just a matter of creating the file, make sure that it's writable. Then you're going to call minidump with the handle to the remote process, the PID, and the handle to the file. So this is pretty straightforward code, and it allows you to actually dump LSAS pretty straightforward. So if we look at it from a Windows API perspective, we have minidump, write dump, we have open process, we have create file, and we have the call to minidump, which was actually just resolved later on, earlier. So, sorry. If we look at the hook API, you'll notice that there's basically none of them that are actually hooking here. So you may assume that this code will run without any issue. The reality, as I pointed out, is that this code in the background is actually going to be hooked because they're hooking the lowest possible point in there, right? So the idea here is we're going to actually start some code. And this is really important to actually put your hook at the right place, right? So we're going to remove this because I'm actually doing this after we actually did it. I'm just going to remove what we're going to do later on in the video. So what we need to do here is have the main. And first thing that we're going to do is actually perform the cleanup. The idea is that in the cleanup, what we're going to do is restore back the original code in the DLL, right? So if we look at this here, and we show the upcode, all we need to do is find the location of the function that we want to unhook and re-implement that. And you can kind of see this as shellcode, right? This is what we're going to use. So this is the structure of what we need to override. We're going to keep it as generic as possible in this case because we want to make sure that it can be ported and can be used for all of them. So we're going to make sure that the byte here, which is the ID, can be modified in the code that we're going to write later on. So 4C, 8B, D1, B8, and whatever ID we need is going to be added. We're going to totally get rid of the test and jump here because they have no purpose. We know for a fact that we're always going to hit that specific branch, so we can just, get rid of that code to keep it lean as possible. So we're just going to, after we did the move in EAX, we're actually going to just do the syscall in the return. Simple as that. So this is going to be the first 8 byte and the last 3 bytes that we're going to have to use. So the whole patch is going to be 11 bytes actually, which is fairly small and fairly easy to re-implement because as you know, getting the address of this is just a matter of, doing a get proc address and load library. The $1,000,000 question now is, what are we trying to actually unhook, right? As I pointed out, Minidump is not in the list of APIs that are actually hooked. So what we're going to do here is actually just spawn a decore process. API Monitor is a fantastic tool for that. You can actually look for like what's happening in the background. I'm not professional with API Monitor because there's a lot of functionality, but I'll show you the, the core. So what we're going to do here is start a monitor process, and we're actually going to use the mini-dump version that doesn't do anything special. And we're going to look for the PID of Notepad, which is 7848. 7848, right? And we're actually just going to run that. Just let me just actually get the code from there. Let's call it unsafe. Let's compile it. There we go. Here it is. So PID as an argument, and we're good to go. As you can see here, it's not performing the dump as expected, which is fine. And we have pretty much all the calls. Long story short, there's a lot of stuff happening in the background. You can filter it out by looking for, specific modules. So no need to tell you that what we're looking for is probably located in the NTDLL, right? But I want to just keep it as all open because I want to kind of give you a hint on where you know that the code that you're looking at is probably related to what you're trying to find. Remember that if you look at this, mini dump write dump is actually located in dbgl.dll, right? So right now we're seeing all kind of kernel based stuff, and a lot of stuff is happening, but nothing seems to be related to the actual DLL that we invoke, right? So we can just scroll manually or add a filter to try to find some code that actually call that specific DLL. And here it is. As you can see here, we have dbg core, which is usually a good sign that you're getting closer to the function that you were working with. And you can always click on the entry and you kind of get a bit of information. So dbg core address, location, so mini dump, read dump, stream, that looks like, to be related to mini dump. Once again, this is internal inside of the DLL. They just rely on other functions that are not necessarily exposed or not meant to be called directly. So we know for a fact that what we're looking at right now is probably related to the mini dump concept. So NT query virtual memory. If we look at this here, doesn't seem like any of the query API or hook, so that's probably not what we're looking for. There is some query information thread, but this is related to the thread, not memory itself. So as you can see, we know that dbg core is probably doing this. There's something to keep in mind that virtual memory is used, so NT virtual memory, because typically you're going to query the memory before you're actually trying to read it, right? So it is a good sign. And since we're trying to dump a remote process, uh, we're probably going to see, a loop that trying to, query all the memory inside of the remote process, which makes sense because as you can see here, we have quite a lot of calls to that query virtual memory. So once again, it is probably a good sign that this was trying to make sure that all the memory was mapped and we get all the information that we need to kind of move to the next step, which is dumping all this memory, right? So every time you see kind of, the same API being repeated several times, it is probably a good sign that you're getting close to what you're looking for. So as you can see here, there's some write file going on. So it's probably, preparing the file to be written. You have NT write file. Once again, as you can see, it's still related to media dump, read dump, stream, sorry. So if we move to kernel base now because we're just, a level deeper. So we're probably getting closer to extremely low level API. And after we did all the query, eventually we're gonna move to, yeah, here it is. It kind of started slowly. So yeah. So we have NT-query, NT-read virtual memory, and NT-write file. So it kind of makes sense that once again, it queried the virtual memory, make sure that everything is up and ready. Now it's reading that actual memory location, and it's actually now going to write it to a file, which makes sense. We're trying to create a dump, right? So this is pretty much it. As you can see, mini dump, read dump stream, read process memory, which totally makes sense. It's in kernel base, and under the hood, you're actually going to call nt read virtual memory, which is obviously located in ntldll as shown in the little hint box. And if we go back to the list, you'll notice that one of them that is actually hooked is nt read virtual memory. So we know for a fact that this specific EDR is actually hooking that specific API, which totally makes sense because um, if you can kind of guess if it's malicious or not, because if you look at the virtual memory definition, you're going to have an handle to a process, right? So it's fairly easy for them to reconstruct the path to the process based on the handle, so they can easily know that an unknown process is actually obtaining an handle on LSAS, so they can probably just flag that right away. So that's one of the reasons why they're hooking the NT-read virtual memory, because of the structure, and it's kind of easy to get the information. As you can see here, you have the process handle and all that kind of stuff. You have the base address and all this information here. So assume that EDR also have access to this information, so they can kind of guess what you're trying to do and take action based on that. And that's the whole point of the hook. And I didn't really take a look at the hook itself, like what they're doing in the background, which kind of check they're doing. I'm probably going to try to do that in the future just to document it for myself and for you guys. But assume that, they're just relying on this information to take action. That being said, I just want to also clarify a little things when it comes to dumping process memory. Um, there's a lot of change in Windows, and they usually trying to, protect it as much as they can, right? LSAS is obviously a privileged process, which makes sense, right? Keep in mind that there is a lot of process that may actually try to, read memory for whatever reason. I'm thinking of legitimate process like, a CSRSS and that kind of stuff, or, even services because they need to access that specific memory location, right? As an attacker, you don't really actually need to usually target it. So Microsoft trying to, had a little um, limitation that can easily be bypassed, but we'll see what it is. So let me just copy what I just compiled. Mini dump unsafe. Paste. There you go. So mini dump unsafe, and we specified the PID, which is going to be LSAS in this case. 848. So as you can see, this is running as administrator. And as you can see, Windows Defender is doing its thing, taking a look at this unknown process. And after 10 seconds, it was like, yeah, everything is fine. You can run it. As you can see, we got an actual error, which is a access deny error. Even if it's an admin, you cannot dump it right away. And the reason is fairly simple. To be able to dump the process, you actually need one specific privilege, which is called SE debug privilege. If you want to see what privilege you have right now, you can actually always use UMI priv, and you're going to get a list of pretty much all the privilege that exists in Windows, and you're going to get their state, right? As an admin, as you can see, by default in Windows 10, you only have 3 of them. One of them is impersonate a client after authentication. No need to tell you that it makes sense, because as an admin, you're impersonating the admin, because I'm technically not running as admin. I was running as dev user. So you need that privilege. And you can actually rely on that privilege to grant you more privilege, as weird as it sounds. Same with the create global object. You can kind of create a privilege object because you were granted with that privilege. So they kind of give you everything to get yourself what you're looking for. They just don't give it to you right away. I'm assuming once again it was probably a security measure that they kind of put in place. It's like if you don't know what you're doing and you're just running the tool vanilla, you may actually not be able to do it because you don't understand that specific little details here. So keep in mind that SC debug privileges is disabled by default. If you guys are interested, I can probably talk about it in a different session, how you can actually grant yourself privileges. It's actually really that simple. You just modify your own token and you actually had it. You'll be able to do it because you have those privileges here that actually allow you to do it. For the sake of the presentation, I'm just going to use a simpler trick, which is called use psexec. Psexec allow you to actually spawn a process as system with the -s switch. So in this case, I'm actually going to run cmd as system. And as you can see here, who am I? I'm actually system. And if you run the same command, which is who am I priv, you'll notice now that I have much more privilege are enabled, including the SE debug privilege here. As you can see, it is now enabled. So if we run the exact same command, oops, which was, let me just grab it from here. I'm literally just copy pasting it. And you wait a couple of seconds. Because, you know, deep learning or whatever they want to call it is still trying to understand. Fun fact, as you may know, I'm actually re-recording the first part because we had a crash exactly for that reason. Sometimes for whatever reason, it doesn't like to be dumped and it just, you know, take forever. And it ended up crashing my main host. That's why I'm actually doing it in the VM this time instead of actually doing it in the live system. I don't want to, you know, lose the recording one more time. So it may have crashed for whatever reason. Or it's just maybe super slow. Sometimes I've noticed that it's just like super slow, especially in this super fast computer. As you know, my environment is running on super old hard drive, no SSD. So it may be a bit slow. So yeah, while it still run, let me just check for fun if the file was actually updated. As you can see, the file is in progress. It's just like 0 byte for now. And a fun fact though, there's an EDR in place and there's, you know, this Windows Defender thing going on. And as you can see, it will successfully run. Nowadays, this is pretty popular that they're not going to prevent you from doing your thing. They're just going to report on it. As an attacker, this is good because if you're facing a company that do have a lot of monitoring, but they don't actually take action, it's going to not change much. So they can have the next gen EDR in place if they don't look at what's happening with it. There's kind of no point, right? It's pretty rare that you're actually going to be blocked. So technically, at some point, this will work, even if it's not patched or it doesn't do anything special. It's just, you know, dumping the memory as expected. So this is the kind of behavior that you have to keep in mind. If they don't look at their log, you can probably generate a lot of noise and you're never going to be detected, right? But yeah. So the idea of what we're going to do later on is to actually implement the cleanup before we actually run the mini-dump code. So this will remain the same, and this is the major plus when it comes to using patch instead of direct syscall. As you saw in the previous session, doing direct syscall can be a bit painful because there's a lot of undocumented information, like, you know, the object attribute structure and that kind of stuff that you have to understand all by yourself. The idea here is we're actually technically doing a direct syscall in the sense that we are making sure that the syscall was not modified. So you can still basically use your default code without having to make any change to it or use the NT version of the API that is just much more painful. In a nutshell, keep your code as it is and make sure that all the syscall that you're using in your code are going to be patched. So you're making sure that the syscall is intact and the integrity is there. It's literally going to achieve the same thing without having to deal with you know, all the trouble of understanding those unknown structure and undocumented API. Um, and as you see, you can always refer to to what we have here. And I'll be more than happy if you guys can actually run the hook finders in your own instance. So if you have access to more EDR, it will be really nice to actually have a list of all the hook API, so we can actually take action in the future based on this actual list that is accurate. So if you guys have instance, just let me know. And if you have any question, we can probably tweak the hook finder if the footprint is slightly different for the EDR that you have. But I'll be more than happy to actually get a massive list of all those hook API. And here it is, finally, 7 days later. As you can see, memory endall is now set to something and the process was completed. If we look at the other one, you see the process endall was 0 and we had a access deny error. This is all happening because we now have the right privilege to do so. So once again, you can grant yourself the privilege. So never assume that as an admin you have all the privilege that you need. Um, elevating yourself as a system is usually a good way to make sure that you'll be able to do anything you want to do. The only difference in this case is we obviously triggered an alert, and we're going to see it later on that we successfully triggered an alert, but with the patch version, we're not going to get any alerts. So the next step is going to be to actually write the code, and this is where this video will stop because you can just look at the part 2 video from there.